So hi everyone, you can hear me? Okay, so, well, good afternoon. We're going to talk a bit about 3D and display stuff applied to some nice computer board that you might have heard of, which is a chip. So first, let me introduce myself. I'm Maxime Ripard. I'm working at Free Electrons for like 5 years. And we specialize mostly on embedded Linux development and training. And I've mostly contributed to the Allwinner support in the kernel, for which I am a co-maintainer. And so, as such, we've been contracted by Nexthing to work on their kernel support on their chip, which I'm going to present. So the chip is a $9 SBC, so it's a very small board. You might have seen it already. For those of you that didn't, there's like the Nexthing guys that hang around. I'm not sure if they are here, but they're like somewhere in the conference giving away chips. So if you want one, just go there. Yeah, there's one here. The chip is based on an Allwinner R8, which is basically just a new label to an old SoC. That is the A13. That has been the SoC on which we started the mainlining effort 3 or 5 years ago now. I don't remember. So it was already, well, it's a rather old SoC, but it was very well supported in the mainline kernel now. Because we basically worked on it for 4 years now. And so it has a 1 gigahertz Cortex-A8 CPU, so something that was a standard like 4 years ago. A Mali 400 GPU, and then a lot of controllers to do P-volume, I2C, SPI, and so on. It's initially some SoC that is targeted at low-cost tablets, so it's mostly oriented to the multimedia stuff, so it has a decent GPU, VPU, a good display support and everything, but you won't find some industrial buses or whatever in it. So yeah. And so we've been working on mainline, on top of mainline, on this SoC. So you might have heard of the poor reputation that Allwinner has with regard to their software in general and kernel in particular, especially when it comes to software licenses and blobs pretty much everywhere. So we basically just ditched all their BSP away and took the mainline kernel that was already working quite well and started from that, adding what was missing. So as I was saying, there was already a significant part of the work that was already done. So things like all the basic infrastructure of the SoC, basically. So the clocks, interrupts, timers, storage support, all of that was already done. But we were still missing a few features that were required for some kind of like regular usage of a board. So we were missing audio that was already done last summer by some Google Summer of Code student that worked on it. So we had some code that was running on top of mainline, but it was still not merged. So that one was the easiest. And then we were missing as well the NAND support because the chip is using a NAND. All of the other boards that supported some kind of storage on the Allwinner SoCs were using MMC, which was working, but NAND was not. And it had some interesting developments that we needed to do for Linux as well, because the NAND used on most Allwinner SoCs are MLC NANDs that are are completely not dealt with in MTD, which is a framework in Linux dealing with the flash in general, and NAND in particular in our case. So we had to develop the whole MLC support for UBI, FS, for example, and MTD, which was quite nice. But Boris, my other colleague, is giving a talk today about it, and he's probably going to talk about that way better than I can. And the last thing that we were missing was a display. And when it comes to having a computer, or at least something that you market as a computer, being able to actually display something is nice. So this is why I focused on. Yeah, and so we had also a bunch of board-specific developments that were related to how the chip was made and not which SoC it was using. So for example, we had the Wi-Fi regulators that were kind of not really wired in a weird way, but the Wi-Fi chip was using so much power that we needed several regulators in parallel to be able to power it. And it was something that was not taken into account in Linux at all. So we worked on that. We also worked on the deep spec, which is the chip capes that you might have seen in the other room in the earlier the session just before. Yeah, so we basically did a lot of work to deal with what was missing. And so my side has been mostly on the display, and it's what I'm going to detail in my talk. So when it comes to displaying something in Linux, you actually have several choices. So you have several frameworks to deal with it. The first one is AVDev, that you might have heard of, which is for frame buffer devices, which is kind of the legacy one. It's the one that has been around for like 15, 20 years maybe. And then you have the newcomers that has been around for quite some time now, but is actually becoming the default now, which stands for not digital right management, but direct rendering manager, which is the one that we used. And so you have more exotic ones that might be used for display, but are irrelevant these days. So V4L, for example, might be used, but it's mostly to be used for actually video pipelines, so captures, and so on. And so display is one of its use, but it's not really made for it. It's more of a hack if you use it. And then you have some framework that I've seen like a single driver that is called Aux Display that has been around for like 7 years and has a single driver in it. Yeah, it exists. Yeah, so I'm not exactly sure why it exists in the first place, but it does. So yeah, so we're mostly going to be talking about, at least in the next slide, AVDev versus DRM, because it's the only actual choice that we might have. And so DRM is actually actively maintained. It's actually very nice when you want to control a video pipeline with several components. It can deal with it. It's widely used these days by basically every component of your graphical stack. So X, Wayland, you name it, Qt, and so on can work directly on top of KMS. And so it had a lot of advanced features, and so it's the default these days when you are dealing with a display engine from a modern SoC with several components that we are going to see a bit later. And so AVDev is still widely used, but mostly for historical reasons. It's maybe not deprecated, but close to. So for example, I'm not even sure that they would accept any new drivers that might be sent. And so it was working pretty well. It's actually pretty simple, but being simple, it just lacks all the controls that you might have in a modern display engine. In an SoC, for example, you don't have any control over the hardware cursors, sprites, overlays that we will get back to that. But basically, it just doesn't work anymore with the SoCs that are quite recent. Yeah. So obviously, we're going to talk a bit about DRM KMS because it's what I used. So DRM stands for Direct Rendering Management and was mostly introduced to deal with graphic cards with GPUs. So initially, I think that's Intel that worked on it. And now it's used by pretty much everyone. at least when it comes to cards with GPUs. And then a new framework came in, which is KMS, which stands for kernel mode setting, which is a subpart of the DRM API that you can use to configure your video pipeline and actually display something on the screen. And what's quite funny these days is that even though it started as a framework for GPUs and it's stored under drivers GPU DRM, you have some drivers that don't even have GPU support, or for SoCs that don't even have a GPU in the first place, because KMS is very relevant to display engine, even though you don't have a GPU at all. So it kind of grew outside of its initial scope, which is nice. So you basically have two different controls depending on whenever you want to talk to the rendering API or the mode setting one, which are two different files in dev DRI, so render and control, respectively. And so KMS will be able to provide you a standard API to be able to control the display pipeline of your embedded system or graphical card. Yeah, and so this is what we are going to talk about. So the pipeline in KMS looks like this one. So you have several components chained together in your system. So the first component that you might see and you actually control and use from user space is a frame buffer. So the frame buffer is basically just like a memory buffer in which you will throw whatever you want to output on your system. And the frame buffer will be associated to what's called a plane in KMS. So a plane is basically just like a layer, and you can have several of them or just one of them depending on your system. So, and you will have associated to that layer at least one frame buffer usually, but you might have several of them, especially if you're doing some double buffering, for example, or triple buffering. You will, for example, end up in this case where you have two frame buffers that will end up always on one plane, but you switch from one to another every frame you send. Yeah. So all of these planes are assembled and muxed together by the SCRTC on your system that will generate a raw image coming from these planes and pass this image to what's called an encoder. So once again, you can have like several CRTCs, several encoders, several connectors in your system. So it gives it to an encoder that will encode that frame that the CRTC just generated and pass it along to what's called a connector that will actually output that encoded frame to whatever is in the other side. So it might be an HDMI output, it might be a raw screen using a parallel interface, you name it. It's also dealing with all the EDID things, for example, to retrieve the resolutions that the screen connected on the other side is able to deal with, so that all the pipeline is configured properly. So yeah. I forgot to tell you, but if you have like any questions, like ask them right now, or something that you want to like explain a bit better than I do. If you are, it's probably going to happen, but yeah. Yeah, so I think I told everything. Yeah. And so when it comes to the Allwinner display pipeline, what we have is this. So we have first the display engine that is split in two parts, which are called the front end and back ends. So the back end is mostly what's the raw feature of the planes. So you have several planes that you can set at different resolutions, and then you are just passing them along to timing controller that is basically our CRTC that will assemble them, pass them to either directly to an LCD panel because it's able to directly generate the timings and so on to be able to drive a panel. Or it will pass it along to another hardware block that is called the TV encoder that will encode the data to either a composite output or VGA1. So depending on the screen that you are using, you will basically use one route or another. And so, in the display engine, you also have a front end that you can use to do some upscaling, conversion, color correction, and whatever. But since we only started to actually work on the display and its advanced use cases, it's not supported yet in the patches I did. But eventually, it's probably going to happen. And so if we try to map that to the concept that KMS exposes, so our display engine would mainly be the planes, but it has some kind of configuration that usually belongs in KMS in the CRTC. Then you have the timing controller that is mainly a CRTC, but since it's able to output directly to a parallel bus and drive an RGB panel, it's also a bit of an encoder and a connector. And then the TV encoder is, an encoder this time. And the composite panel, the composite output is actually just a connector that actually doesn't even do anything besides just saying that there's a dumb connector that just passes the frames along. So that's our view and our mapping of the IP blocks in KMS. And so if we look at the DRAM stack, mainly from a system point of view, the system is going to look like that. So we have the display engine and TCON, timing controller and TV encoder that are just here. We have our DRM driver just above it that drives it. The API that we are using to communicate with the user space, or at least the user space uses to communicate with our driver, is KMS. And it's going to use a library called libdrm to talk actually to our driver. And in the end, it's going to be used by an X11 plugin that then X is going to use to be able to display applications in your system. So obviously it makes the assumption that you're using X, but yeah. So this actually works until you want to create buffers in your system. And then you need to be able, from the user space, to be able to allocate new buffers of memory that you can use to pass to the display engine, and that the display engine will be able to take and access using DMA. This is done using an API that is called gem in Linux, which is basically just an extension of DRM, which is part of the DRM ecosystem. So it's something that you have to support usually in your DRM driver. But what's nice about it is that the memory that can be allocated for video buffers in your SoC, usually it's just plain memory coming from RAM that doesn't have any particular restrictions, or might have, but at least it's not stored in a separate RAM bank stored in the GPU or graphic card, like it's, for example, the case in x86, or at least on real graphical cards from NVIDIA or AMD. And so you can rely on CMA, and you have a default implementation for gem that relies on CMA. And CMA in Linux is the contiguous memory allocator. And just like its name states, it allows you to allocate contiguous memory area in your RAM. And so it was made in the first place to be able to allocate big buffers, especially big buffers, because we already have contiguous allocators in the kernel besides CMA. For example, the default one, which is kmalloc, allocates contiguous buffers, but you have a limit that is, I think, at 512 pages, which is 2 megabytes on ARM. So when it comes to video buffers, it's actually quite low. And during the life of your system, you have usually memory fragmentation, so even after a while, it's difficult to be able to allocate using kmalloc 2 megabytes directly. So CMA was made to be able to deal with this kind of huge memory allocations, so usually in the tens of megabytes or something like this. And so it works by just reserving memory at boot, allowing Linux to still put some caches mostly. In this area it reserves, and then when the driver comes in and starts to request memory, big chunks of memory, basically Linux just flush the caches, takes the memory back using CMA, and pass the memory buffer along to the driver, and everything works. So we have, in KMS at least, an interface that is able to allocate what they call dumb buffers, which is usually the default buffer that you will use. That's using gem and CMA, at least in most ARM SoCs and drivers. Except that dumb buffers, at least in the documentation and what they expect, are not meant to be sent to the GPU. Or at least you have no guarantee at all that the GPU is able to access a dumb buffer. So if you actually want to be able to allocate memory in which the GPU can render, you will need to declare a new IOCTL in your driver to be able to do just that. And that's going to be used directly by your X11 plugin. So that's why you have this error here from X11 to gem. So for example, in the Allwinner SoC, it's mainly just an interface problem. Because we basically just use the same function. We don't have any kind of restrictions on what the GPU can access either. So we basically call the exact same function that the dumb IOCTL calls, but we have to create another one just because of the semantics of the IOCTL. Yeah. So once you have the buffer, you can allocate a new one. You will be able to render in it, but usually you also want to share your buffers with a bunch of other devices, like an ISP, for example, or you want to just grab the picture that was taken by your camera and display it on one of the planes directly without any copy or anything. And in which case, you have a framework that is already able to do that in Linux, which is called DMA-buff. And you have another glue on top of DMA-buff that comes in with the ARM, which is called Prime. And it's also the name of the interface you want to interact with when you are in user space. And so basically, Prime is made to be able to share gem buffers among several devices. So yeah, and so there's a default implementation when you realize, once again, on gem and CMA to be able to just have Prime and DMA-buff working. So you usually don't have anything to do except if you have some fancy memory model, and yeah. So now we are able to allocate buffers, make the GPU render in something, in one of those buffers. Actually, I forgot to tell something. Usually the GPUs, or at least the Mali, have an MMU of their own. So they could theoretically be able to use any buffers, not especially contiguous in your system, to be able to render, because they have their own memory mapping and they can have a virtual mapping that is contiguous and work on it. And the issue lies, especially when you start sharing buffers along devices, because in the simplest, it starts to change a bit with the I/O MMUs, but on systems that don't have any I/O MMUs, the other device usually don't have an MMU to access the memory bus. And so you will have to allocate contiguous buffers for these devices, even though you like do the GPU rendering, if you want to share the buffer with some kind of other component in your system, for example, the display engine, for example, it has to be contiguous for the other to work, but not really for the GPU itself. Yeah. And so now that we have some kind of infrastructure to be able to display frames, to be able to allocate buffers in which the GPU can render, to be able to share that buffer with other components in your system, other hardware blocks, we can start actually working on the GPU integration. And even though it sounds like the hardest part to work on, it's actually the easiest. And we'll talk about that. So basically, we have two solutions here. So the GPU found is in most of the Allwinner SoCs is the Mali 400 from ARM. So depending on the SoC, you have different number of cores, but it's always the same GPU itself. And so you have basically two options to support the GPU. The first one is Lima, which is reverse engineered proof of concept. I wouldn't call it a driver. And it's basically the Lima development that triggered all the other reverse engineering efforts that happened like in the last few years. So at Naviv, Freedreno, there's probably some others. I think there was Great at some point as well for the Tigra GPUs. Yeah, anyway. Sorry? Yeah. So from like an ethical and general mainline friendly point of view and everything, Lima would be the perfect solution, except that for 2 years the development is basically stalled. So it's never actually been like a real driver that you can use with a real OpenGL implementation and so on. So it's not really usable as is. So we had to turn to the other solution, which is the ARM provided support, which obviously works with most of the features of the GPU, and comes in two parts. The first one is a kernel driver that you have to integrate to your Linux kernel that is licensed under the GPL, and you have access to the sources on the ARM website. And the second one is a proprietary OpenGL implementation that lies as a blob in user space, which is just a library that applications will link to, and will be able to use OpenGL in your system. And so the integration will be done this way in your system. So you're going to have, at least from user space, just the OpenGL ES implementation that uses some device file that is called dev Mali to communicate with a GPU driver that will use DMA-buff to communicate and exchange buffers between the GPU and the display engine to be able to actually display those buffers. And we'll talk to the GPU itself because it's like its main purpose. Yeah. So everything is provided by ARM on their website. So that is if you are lucky enough. In our case, so for the Mali 400, which is called Midgard, I think, you had a GPL kernel that was available that you could compile and so on, which is fine. But the library implementation they provided was only compiled for ARM 64, which was not really working for us. So we had to turn to at least Allwinner so that they could provide a library that was compiled for ARM like 32 that we could use on our system. And so it's a bit of the part that is like not so nice in that you have to depend on someone to give you the right binary blob, otherwise your system doesn't work. And on the driver side, you basically just have to create a platform glue that will just make the GPU be able to run on your SoC. And then you just like tell the driver to go ahead, and it's just working. So in this driver glue, you basically have to deal with mapping the memory to be able to access to your GPU, retrieving the interrupts, enabling the clocks, the reset lines, power domains if you have some. So basically everything that is depending on your actual SoC and how the GPU is integrated into your SoC. And then you just let the GPU itself do the GPU driver do its work, and it's like working. So it's actually pretty cool. Or at least way better than what I was expecting at first when I like grabbed the source code and then what am I doing? Yeah. So it still has some kind of nasty stuff. For example, it won't compile in 4.4 and later. Well, it will not run. Because if you're familiar with how you're supposed to access memory from user space to the kernel, from the kernel, you're supposed to add accessors which are copy to user or copy from user to be able to access memory from the kernel to user space, or the other way around. Except that on ARM, before 4.4, you could just like dereference the pointer itself, and it was working, which apparently they did. So since 4.4 it doesn't work anymore, we added some extra protection. And so if you just like have this configuration option enabled, which is a default, as soon as you will start using the GPU, your kernel will just panic and explode because you just tried to access a page that was like not supposed to be accessed directly without the calls to these functions. So yeah, it's not perfect, but it's like the best we can have anyway. So, and so once you have that GPL driver running, you put the blob in there, and you need to have some X11 magic to be able to like use your GPU. So we have and your display driver, obviously. So there's a generic driver that is called mode setting, that is, so XF86 video mode setting, that is working on top of KMS, which is a generic API, so it works pretty much everywhere as long as you have a KMS driver. And so this works fine, except that it has the assumption that it's supposed to rely on Mesa for the rendering and OpenGL stack, which is not our case. So ARM developed a video driver that is called FX86 Video ARM SoC for basically all the SoCs that are using a third-party GPU, so like the Mali, the PowerVR, the Vivante one. So basically all the SoCs besides the NVIDIAs and Qualcomm's, I think. And so it relies on KMS as well for the display side. And it relies as well on driver-specific IOCTL to be able to allocate buffers, like we've seen a bit earlier. And then it just relies on the vendor-provided OpenGL implementation to be able to, like, for the applications to draw directly on the buffer. And you just have to write a small glue to that driver to be able to allocate that buffer using that driver-specific IOCTL and give some hints to X about what you are actually able to do in your system. So, for example, can you use an hardware cursor or not? Can you do some asynchronous vblanks to be able to switch buffers and so on? So it's just a bunch of flags and functions. Overall, it must be like maybe 100 lines of code, so it's actually pretty small, but you still have to write it. So yeah, that's pretty much it. I ended up a bit earlier than what I was expecting. So yeah, if you have any questions, go ahead. We have some time. Yeah.
I have a question about the Mali support. So you say, I don't know anything about it, but I have a very naive question. ARM seems to be like pretty involved in Unix development, if I'm not too mistaken, with Linaro, and everything, at least on the CPU side.
Yeah.
Why would, for the GPU side, why would they not really be involved in?
Is there any ARM employee in the room?
I don't know. I mean, do you have any guess, maybe?
I don't know.
Can you repeat the question?
So yeah, the question was, ARM seems to be pretty involved in the Linux support on the CPU side. So why is it not working on the GPU side? And I basically have no idea. So there's been a bunch of blogs on the internet, so you take it as like you want, stating that the issue is actually the manager of the GPU division. I basically don't know anything about it, but that's like...
So for Mali 400, they
Yeah.
bought the technology, so they don't
Oh, okay.
own everything on it. For
Yeah.
600, they do own everything, and that might become open source.
Okay.
But they have been this month releasing new binary blobs that are actually redistributable. So
Oh, nice.
you can now hand people your Mali blobs, which is a big improvement.
Yeah,
Still
because...
not enough, but you can at least now give people.
Yeah, it's something that that I forgot to talk. Yeah, the binary blobs that you find on the Linux, on the ARM website is not something that you can distribute by the license. So you have to have an agreement with ARM, which is something that usually you can do when you are an SoC vendor or if you have contacts with the SoC vendor. But if you are an individual, like it's not happening. So yeah, it's good that the license changed. Okay. Any other questions?
So now that you figured it out, how long did it take to some other SoCs? I mean,
So the whole display part, or
just the board support, like say another SoC.
so it took me something like 6 months, I think. But I was like oblivious to all that display stack before, so it was not really experienced or anything. I had some help from one of my colleagues that already did it, but still it's not as if you already wrote one and so on. It takes a lot of time to get all these concepts right, a lot of questions to some experienced developers. So yeah, it took me a while, but it would probably be much faster now.
Through the entire process, what would you rate as the most difficult aspect of it all?
I'd say understanding the expectations of DRM, well, and KMS. So like getting the concepts of everything is pretty easy. But then you have like a lot of callbacks that you need to write in your drivers. And the fact that there's so many different memory models, expectations, and so on from the GPUs, cards, and so on, it's actually pretty difficult because you don't have just a single way to do things. You have so many ways that you just get lost in all of them. So it's actually what has been the most difficult for me to get. Once you know what you are doing, then it's easy. Well, not easy, but easier.
So my understanding was that DRM KMS is one of the better documented things in the kernel as of recently. Was it helpful, or is it still not quite enough to?
It was helpful, but I don't know how you code. But at least when I code, I tend to mostly like read some of the code from the drivers and everything, and like. At the time, it seemed to me like a free-for-all and everyone doing like completely different things. And so it was kind of difficult, yeah, to see what you were supposed to do.
There is no single driver, at least simple driver that can be used in reference. All of them have slightly different implementations and slightly different mistakes because of historical reasons.
Like everything else in kernel.
Yes.
Maybe on the docs, what we try to do since maybe about a year, 1 year, is add examples in the docs about how you do it for a specific case. Like if you have run back here, this is how you do it in your kernel mode setting sequence.
Yeah.
So if you have any squalls there, point to raise them or you can bring patches.
To be honest, I don't have any suspend or runtime PM support right now, so.
Yeah, those kind of things.
Yeah.
We really like to do that. And we also have in the DRM subsystem special support for kernel docs so that
Yeah.
But it's hopefully going to land in upstream real soon, so you can nice code examples and all that.
Okay. Yeah.
That would be really great.
Yeah, I'll try to do that. Yeah.
Easy question.
I'm not too sure about that.
That you had to write a platform glue layer for the Mali driver.
Yeah.
For plugs, SIM cards, memory. Why isn't that abstracted by DT?
It is, but like, so the whole platform glue thing is basically just a hack. So the Mali driver itself is loaded using a platform device style loading. So the glue, at least if you want, so there's some kind of DT support which is completely broken and doesn't even compile. So you don't want to use it. But you have some kind of a platform mechanism as well where you can basically just load a C file that is just going to be used for your platform. So that actually works pretty great, except that you have to register the Mali platform device yourself. So the way I did, I don't know if it's the way it works, but like it seemed to work a bit, is that I basically just have, so you have a hook in each platform stuff that is called during module init. So the way I'm doing it is that during this module init hook, I just like parse the whole device tree and generate the resources for the platform device that's going to be loaded, and then it's going to be like executed by the driver. So it's, yeah, kind of a hack.
Or you could just have that your glue driver match the DT node for the Mali CPU and then create.
Yeah, but then you would have to have a probe of your own, which is like in the common.
You want for a function and that creates another platform.
Yeah, probably. But you can't have two probes actually in a single module.
Could be too much.
I think
Yeah.
that's how the MUSB driver works. You write a glue, it probes, and then after all the glue stuff, you register the actual MUSB device.
Yeah.
I don't know about you, but I want to use MUSB for any kind of reference.
So yeah, it's kind of not that great from a like kernel maintainer point of view, but like if you,
In theory, ARM could just fix that and have probably DT well.
yeah, I think, as long as you make like, it's kind of difficult because then you have different assumptions from one SoC to another. For example, one might have some reset lines, not the other, or you might have two different clocks for the like memory bus interface and then to actually drive the GPU or not. So it's kind of made difficult, but it would be doable still. Yeah.
So you mentioned the suspend, resume, runtime PM stuff. Is that just something that you haven't done on your side yet, or is that a limitation of DRM KMS?
I think it works pretty great on DRM. It's just something that we haven't spent time on Allwinner SoCs at all yet. So it's my fault, not theirs.
Did you hurt your arm doing this project?
Kind of. I broke my wrist while working at Necting like 2 months ago. So yeah.
Stay away from hamburgers. Were you doing the Oculus Rift on the hoverboard?
I would have liked that. No, I didn't have anything but an overboard. I mean, I don't have any excuse. No more questions? So, well, thanks for attending.